How do you remember where you parked your car and the face of the loved ones, or even what you were just about to say? Memory is one of the most essential and still mysterious function of the brain. Our next speaker is working to uncover the deep mechanism behind how we remember, how we predict, and how we make sense of the world. Ila Fiete is a blazering neuroscientist who brings the tools of mathematics, physics, and computational modeling to the complex questions of the human minds. Her work explores the very architecture of memory, from error correction and integration to the precision neural codes that guide us through space and time. She received the 2022 Swartz Prize of Theoretical and Computational Neuroscience for her pioneers' research on grid cells, the neuron that helps us navigate the world. Her discoveries have shown how the brain turns experience into maps, helping us build and stabilize spatial memory. Dr. Feld earned her undergraduate's degree in physics mathematics in the University of Michigan and completed her PhD in physics at Harvard University. We still like her regardless, though. She currently serves as the professor of MIT Department of Brain and Cognitive Sciences and associate investigator at the McGovern Institute and director of the Yang Icahn Center, where she continued to push the boundaries of what we know about the brain's inner working. Please join me in welcoming a scientist who is helping us decode the mystery of memory, Ila Fiete.
Thanks very much. All right, so a bunch of you walked into this building today, and you probably got introduced to a bunch of people, right? I don't know how many of you remember many names. If you're like me, you probably don't. So we all, think about memory. We all worry about memory, right? But I will say you all have phenomenal memory powers. You can meet a friend who you haven't seen in decades, or just run into them and recognize them. You could probably, each of you, tell me about an experience that you had in your childhood, maybe decades ago, and it only happened once, right? And so these kinds of memories are called autobiographical memories, like what happened, where did they happen, whom did they happen with, what were you saying, and so on, right? And so it's not just us that have these phenomenal memories. Birds have them too. So this is an example of a bird called the Clark's nutcracker. It's a jay. And what these birds do is that in the fall, they start saving up food for the winter, for the coming winter. So they'll get pine nuts and cache them away, like of order 10,000 seeds in the fall. They'll cache away, store them in the ground at about 2,000 different locations. At the peak of their caching activity, they'll put pine nuts into 100 different sites in the forest. And they'll do this over a radius of about 20 miles. Okay? And come winter time, they actually are able to accurately find and retrieve those nuts, which is essential for their survival. It's amazing. And it's notable that the ground, of course, is quite snowy in the winter, so it looks quite different. So it's not just memory, but it's also inferring from partial or memory of something that looked mostly similar, but not quite similar to what things look like now. Just like seeing your old friend after many years or decades. All right. I just want to tell you one more amazing thing about episodic memory, besides the fact that we have such tremendously good ones. And this is actually, it's a trick that you can use using your episodic memory, which you can leverage it to quickly memorize a sequence of new and completely random items. Okay, and in fact, it's a trick that's been known for millennia. It was first described, as far as we know, by Cicero, and it's also a trick that's used today. So the memory athlete, Clemens Meyer, who was a world memory champion, used a path that he took through a familiar place, his childhood home, and used that path to then store a memory of a bunch of a big set of shuffled cards to then be able to remember that shuffled deck of cards very shortly after when he had to recall them. So this is a conundrum, right? Which is, why does adding, so if you want to memorize the order of a deck of cards that's been shuffled, why does then associating that sequence of cards with the sequence of places that you visit on a route actually improve memory? You're adding to the memory burden, right? So why does that make it better? So this is a question that we've been thinking about for a long time, and my group has recently gained some insight. So we just explained how, first of all, the circuits of the brain might support episodic memory, and also the same understanding provides a solution to this conundrum of this memory palace and how it's used by memory athletes. So we just published this paper last month, and basically trying to pinpoint what is it about the circuitry that allows the brain to sort of do this memory task. So by the end of what I'll tell you, I hope I will convey to you like implications for how you can remember, but also how these circuits relate to dementia and Alzheimer's, and also potentially to AI. Okay, so that is the behavior. Now here's the brain. So the brain, the part of the brain that is involved in the central player in storing these episodic biographical memories is this beautifully structured circuit, the hippocampus, and it is the thing that binds the what, the where, and the how with the whom. Okay, and this picture is actually from the mouse brain, but the circuit is strikingly similar in the human brain. Okay, and so the same circuit, mysteriously, is involved in spatial memory as well as in episodic memory. Okay, so these, these autobiographical memories. So let's just, look at some of the parts of the circuit and how they work to try to understand how this circuit and the brain give rise to what we call the mind. Okay, and so what is the mind? So I define the mind as the brain is generating internal representations that are stable for abstract concepts, right? That are not directly just perceived from the world. Okay, and so what do I mean by this? So let's give an example. So here you see a picture of Maybrit Moser. She's the 2014 winner of the Nobel Prize in Medicine and Physiology for finding some of the, for discovering grid cells in the brain, which are involved in spatial memory. And she's placing here a rat into an environment which is featureless, this black walled environment, and recording cells from that animal as it's running around. So the animal's running around. It does whatever it wants in the environment. It's a featureless space, just plain black with black walls. And it might scratch itself, might forage for scattered food, pellets, it might just pause for a bit to eat them, or it might rear up on the wall, as you see in this picture over here. Okay? And as it's doing this, we can look inside a circuit, okay? And this is a circuit that has about, several thousand neurons, 2,000 to 3,000 neurons, and we can look at the states that are present in this circuit, okay, as this animal is doing this very rich behavior. And every dot here is one, is a state that the circuit is in at one moment in time. And all the different dots are all the states the circuit ever visits over all of this rich behavior. And I think you could have seen, you saw from that video that the states only form this one-dimensional ring. It doesn't do anything more than this simple one-dimensional ring. So what's going on in this circuit? What the circuit is doing is it's building an internal compass, okay? And in real time, it's tracking the direction in which the rat's head is pointing. So previously I showed you the set of all the states, right, these blue dots, that the circuit is traversing over time. And now this purple trajectory is showing, how the states are evolving over time as the animal is actually running around, doing its foraging and doing its thing, right? And we can just look at this for a bit, and you can see that, here the animal is just sort of, locally, probably mostly facing the same direction. These different points here represent different angles that the head direction, that the head is facing here. It just did a quick turn because the state moved all the way to the other side. So basically points on this ring correspond to angles, right, in the world that correspond to this compass direction where the rat is facing. Okay, So let's okay, so to show you that this is true, to convince you that's the case, here on the left, I've taken that same set of points, just a different projection, so it looks more circular, just a different, different angle. And I've colored every single point here, okay, all of these states of this brain circuit, with just a continuous coloring along this mental ring, okay? And now on the right, I color the exact same dots now, but with the different coloring, and this is a coloring that is based on the physical direction that the rat's head is facing as we measure it with an LED on the rat's head as it's moving around in the space, okay? And you can see the correspondence of the colorings is almost identical, right? They're almost the same. In other words, the states on this ring are really representing the directions of the head of the animal. I haven't cheated. There are some subtle differences which will convince you of that. Actually, one of these 2 points are slightly different in color, if you can see, pink versus purple. Okay, and so what this is indicating is the animal, cannot and does not have a perfect estimate of the angle, okay, the degrees in the world where it's facing, because there are no degree markings on the walls. It doesn't get that information. It has to infer, I've turned this amount, or I've turned, more or less, right? So it's estimating which direction it's facing as it's doing this behavior. So the same circuit is also active in completely non-spatial settings. These states are completely internally generated, which you can see because the blue dots are the dots that I just showed you, and the green dots are the states of the same circuit in the same animal as the animal is doing REM sleep. Okay, and you can see that these green dots lie completely over the blue dots, which means that they're internally generated by the animal's brain, and they're online even when the animal is fast asleep, right? There's no external sensory input from the world. So that means these cells are not merely spatial, right? They're really these internally generated abstract constructs. All right, so these spatial, the reason I'm telling you about these spatial states is that this circuit is involved in spatial representations, but these representations are more than spatial. It turns out that these spatial representations scaffold a memory system, this memory circuit. Okay, so here are these spatial representations. I've called them grid cells. What we saw just now were head direction cells, but grid and head direction cells together scaffold the circuit and create a set of these states that are low dimensional, invariant, and stay the same over time. It's kind of like a clothesline, clothesline onto which external sensory cues, which is data, the events that you see, the people you meet, can get hooked. Okay, so these are just sort of low dimensional internal states onto which clothing is hooked, and that correspond to external data. Okay, so let me just briefly tell you what this might mean for Alzheimer's disease. So this model where these spatial-like representations are the scaffolds for external inputs that you receive as events in the world and that become your memories, it implies that basically loss of spatial representations should then lead to the loss of autobiographical memory. Okay, so and some observations that we have from the field are consistent with this. So the first behavioral sign of Alzheimer's disease or dementia is spatial disorientation, and in fact, on the brain level, it's these cells, these spatial cells, that are affected first. So the idea is that these could be, early signals, markers of dementias. And so this is potentially what's going on, is the scaffold itself becomes destabilized and twisted, and therefore the clothes can no longer remain or be hung onto the scaffold. All right, so back to the memory palace. So this is the solution to the memory palace conundrum, which is that if you have, okay, so here's how the memory palace works briefly. So first you have a very familiar memory, which is, for example, your memory of your childhood home. So now if you want to remember some new items, you first define a path through the childhood home, and then as you traverse this path, you take the new data, the new items you want to remember, and you place them onto these locations along the route. And then when it's time to recall the items, you just imagine yourself again retracing your steps and simply collecting the items that you had placed along the path. And so it turns out this is not This is not a special gift. This is a trainable skill, and any of you can go and actually learn how to use memory palaces. Medical students do it regularly. Okay, so the final thing I want to say here is that these models can also inspire new types of machine learning and AI. It turns out that circuits built on the simple architecture of this hippocampal system can do better memory performance than machine learning models that are trained using sophisticated techniques. So they can give rise to sort of in the machine learning space the hypothesis that neural architectures are special and empowering for more robust and more efficient architectures in machine learning. Okay, so now when you go to your next event, hopefully when you meet people, you will know how to remember, and maybe you will take the time to look up the memory palace technique. Thanks very much.